All right, so we are getting into rigid body kinetics. So we started that last time. We have a quiz at the end of this class. And I left the quizzes downstairs, but in the last 10 minutes or whatever, I'll run down and get them and we'll do the first quiz. Okay, so we started rigid body kinetics last time. And there are two main equations of motion. They're both vector equations. The first one is Newton's second law. So tell me what that says. If you take all of the external forces acting on your chosen body, we'll call that F net. That is equal to the mass of the chosen body times the acceleration of what point on the chosen body? Yep. Center of mass, right. So the center of mass is this key thing. And this is, it gives two equations if you're doing a 2D problem in the plane, and three equations if you're in full 3D space. And then the moment equation, I abbreviate that rotational Newton's second law because you derive it from Newton's second law. It looks like Newton's second law. This one says, choose some about point A, okay? And then add up all of the moments acting on the body about that point A. Those are vectors. That's equal to the mass moment of inertia about A, how hard or easy it is to get that thing to rotate, okay, times the angular acceleration vector. But this isn't true for every A. This is only true for A that's either a fixed point, I'll call it. So that's a point that's fixed on both the body and in your coordinate system. Okay, so think of that as like a pin joint or a ball and socket joint in 3D. Or the only other option is the body's center of mass. And this gives one equation if you're in 2D because there's only one axis of rotation in a plane. And three equations in 3D. Okay, so from statics, you get really bad habits about choosing your about points because you can choose any point you want, okay? In dynamics, you can't choose any point you want. There's only two if things are moving, okay? Any questions about that? Well, the way it works out is if you derive it from, if you derive this from particles and derive it from Newton's second law, you get to a point where you have this kind of ugly looking thing, but a bunch of the terms cancel away into this simplified form. Basically if certain cross products go to zero and stuff, and these are the points that make that happen. So you can do this calculation for a general about point, but the math is way more complicated. Okay. Okay. A body always has a center of mass, right? Anything that you isolate, I mean, you always could choose B here. you always could choose the about point to be at the body's center of mass, the chosen body's center of mass. Not every body has a fixed point, okay? Like a boomerang flying through the air, there's no point on a boomerang that's fixed. Everything's accelerating and stuff. And so there are problems where you just don't have this option, okay? So why would you even bother sometimes using a fixed point as the about point when you can always just do it? You know, a lot of times I say, let's do every problem, treat it the same way, because it makes it less likely you're going to make mistakes. Well, why not just choose the about point at the center of mass for every problem? In this case, there is going to be a reason. The math is a lot easier if you do have a fixed point. Okay, so we're going to use both of these two options. Okay, that might be a little more background than you need right now, but and now in order to use these equations, we need to define three things that we haven't talked about yet in this class. The first one is the center of mass. And remember, that's the body's centroid for a homogeneous material. And we basically did this last time. And then we're going to need to define the mass moment of inertia. And we're going to denote that capital I with the about point in the subscript. And people don't tend to say mass, although you do have to, in your mind, make a distinction between this moment of inertia and the one we use in D form, which is the area moment of inertia. We haven't gotten to that yet in D form. And then the third thing we have to define is the moment of a force. And people tend to not say this, they just call it a moment. And that's a vector, and I'll denote it capital M sub A. Okay, let me do, well, I gave you a list of the centroids of common shapes last time. I just want to do one simple, use the integral one time, the integral definition of centroid one time in sort of a simple case so you can see where these formulas come from, okay? So, I didn't do this all the way out, so I hope we can get this to work. If not, I guess it's not as stylish, but you still get the idea of where these, well, I don't know, we'll see how far we get. But let's figure out how to represent the centroid of a quarter circle. And we'll say the radius is capital R. And the integral definition, this is just a two-dimensional problem. So remember that the centroid location is 1 over the total area times the integral over the area of the centroid of, so now we're breaking it up into infinitesimal areas, and we're going to multiply the centroid of the of our infinitesimal area times the infinitesimal area. So that's the definition of the centroid. And we want to use that integral to come up with the formula that I gave you last time. Okay, well, in integral definitions and stuff, the key part is always choosing how to break up your areas. Doing this in polar coordinates might be a good way to do it. I was thinking that I would break it up into infinitesimally thick arcs like this. Where the distance out to that arc is lowercase r, and the thickness is dr. Okay, so that shaded region is one of our infinitesimal amounts of area. Okay. And the nice thing about this is there's symmetry. So we know that the centroid of this infinitesimal area is on the x equals y line. That's that's an axis of symmetry here. Do you see that? This is an axis of symmetry. So the centroid has to lie on that line. Oh. So where is the centroid of that thing? I was thinking it was going to be right on that line right here, but that is not the case. It's actually going to be like in a little bit. Okay, so in order to come up with the representation of these two coordinates, we would have to know where that falls. Could we do that? Nothing jumps to my mind right now. Anybody else? Okay, well, I'm not going to do that one then. I'll think about that later. So pretend I never wrote this. Just get this out of your notes completely with your little magic eraser. And let's do a shape like this. Let's say we have a parabola. Okay. And let's say that it has, so this is, we're going to calculate the centroid of this. Okay. And this distance is A. And this distance is H. Okay. And the equation for this parabola is y equals cx squared. Okay, and so I'm going to break this up. So again, like I said, the key step in using an integral definition like this is figuring out how to break up the areas. This one is really straightforward. We're just going to break it up into infinitesimally thick rectangles. Don't worry, Fred, I didn't start to use this for a different shape and then have to quit because I didn't know how to do it.
Very well.
Okay. If I did ever do that, I would, tell you that I had, but I didn't. Okay, so this distance is x. This thickness is dx. And now let's figure out what that c is. There's only one c that's going to make the width a and the height h. So we know that h is equal to c a squared, right? Just plug in those end values into the function. And so c is equal to h over a squared. And so this parabola follows the function a over h over a squared x squared. Okay? And we're going to use this integral definition. So what's the total area of that? So the total area, I guess we're going to have to calculate, is the integral from 0 to a of h over a squared x squared dx. And so that is h over 3a squared x cubed evaluated from 0 to a. And so that is h times a over 3, it looks like. Okay, so that's the total area. Everyone with me on what I'm doing there? I'm just coming up with this total area that we need for the integral formula by just integrating that shape. And so now we're going to use the integral formula. So x bar y bar is equal to 1 over the total area. So that's 3 over HA. And then times the integral of, so first, the centroid of our given infinitesimal shape. Well, the centroid of this green rectangle here is just at an x value of x, you know, and a height of half of y, right? Because it's a rectangle, so it's just going to be right in the middle. So this is going to be x, and then half of y is h x squared over 2a squared, because this is the y value. So the centroid is just going to be half of that. That's where that 2 comes from. And then our dA, the area of that rectangle, is just going to be the height, which is h over a squared x squared times the thickness, which is dx. Any questions about that? All right, so now we have these two integrals. So x bar is equal to 3 over HA times the integral. Oh, I didn't do the bounds, but we're doing this in terms of x, so this is going to be from 0 to a. So integral from 0 to a of h over a squared x to the third dx. Everyone with me on that? We can cancel these h's. And you get 3 over, I'm going to pull the a squared out, so 3 over a cubed times x to the fourth over 4, evaluated from 0 to a. And so you get 3a over 4. Okay? And then for the y, y bar is equal to 1 over the area times the integral from 0 to a of h squared x to the fourth over 2a to the fourth dx. This cancels this. And you get 3 over 2a to the fifth. X to the, so if I integrate that, this is x to the 5, and 2 times 5 gives you 10. So this, evaluated from 0 to a. A to the fifth.
I think you forgot one of the factors of each.
Oh, okay. Thank you. So there's, so up here there's just an h, a 3h. And so now you get, it looks like the x's, when you put a in there, it cancels the a to the fifth, and you get something like 3h over 10. And so now the idea is that now that we've figured these two things out, x bar and y bar, now we don't have to use this integral anymore. We've come up with a formula, and now anytime you want to calculate the centroid of this shape, you can just use these formulas based on the height and the width. Okay, you with me on that? The idea, you don't have to follow all this, and maybe there's algebra mistakes or something, but I just wanted to show you how you go from that integral definition to the formulas, which are the only things we're going to use. Okay, so now we're done talking about centroids. Okay, and the reason that we have to calculate centroids is because there's two possible reasons. The one we have to use is, this is the location where we need to calculate the acceleration in order to use Newton's second law, okay? And then also, we might be using this location as the about point for the rotational Newton's second law. Okay, so the next thing we have to define is the mass moment of inertia. And it'll always be denoted with a capital I. And this is not the same thing as the area moment of inertia. I sub A from D form. And so this mass moment of inertia that we care about measures how hard it is to start a shape rotating, to start an object rotating. A big mass moment of inertia has a lot of mass situated far from the axis of rotation. And a small mass moment of inertia has the mass situated close to the axis of rotation. Okay, so for example, like sports give you a lot of good examples of this stuff. In gymnastics and diving, there are multiple ways to do flips. You can put your body in all these different positions. The two extreme positions that are the farthest from each other are a position like this, looks like fetal position. Okay. And the person's flipping around like that. And the other extreme is you have your body straight out like this. okay? And you're flipping around. Well, so say this is gymnastics and both of these two people are doing double flips, you know? And say this is the same person. Say they do the one on the right first, and then later when they're tired or their last part of their routine, they do another double flip in this position here, this tucked position. It's the same person, so it's the same mass, like everything's the same length and everything. But in this case, in both of these two cases, the axis of rotation is the person's center of mass, okay? So think about in what case is the mass situated close to the center of mass, and in what case is the mass situated far from the center of mass. Here, as much as you can with a human body, you're pulling everything as close to your center of mass as possible. That's what the goal is with this tucked position, okay? You'll even sometimes, I mean, they're supposed to take points off for it, but they don't always, but you'll see people spread their legs apart so they can actually get their knees closer to their ears to get even closer to get everything even closer to the center of mass as they spin, okay? So here the mass is close to the center of mass. And so this is a low mass moment of inertia. Here the mass is, well, you could put some mass farther from the center of mass if you lifted your arms up over your head. I don't know why nobody does that, but it's just not a thing people do. But here the mass is far from the center of mass. That means this is a high mass moment of inertia. And so which one of these double flips do you get more points for, more difficulty points for? The high mass moment of inertia means it's hard to get that rotating, okay? And since it's hard to get it rotating and you can't spin as fast, you have to have a lot more power to complete 2 flips before you land this way than you do if you're tucked. Really good gymnasts can do double flips shockingly low to the ground, you know, if you're experienced spinning fast and everything. But you need to get way up in the air if you're gonna finish a double flip in this laid out position. So that's kind of the idea of mass moments of inertia. Yeah, I mean, you've seen this stuff in Physics 1. Anybody have any questions about that? Yeah.
So like for figure skaters, are they considered like 2-dimensional objects?
Yeah, so from that you'd be looking from above, and their axis of rotation is their center of mass from above.
Okay.
And so yeah, from above, when they're like this, their hands and I guess their legs are out too. One leg. You need to have one on the ice.
Yeah.
And then you're as far as you can get from your center line, which is your axis of rotation. And so you rotate slow, and then when they pull everything in tight, then to preserve angular momentum, they have to spin a lot faster. Also, one thing about that, it's always dramatic at the end of the routines. You know, they do all their stuff and then they get to the end and then they start out stretched, going slow, and then they pull in for the finale and they spin and everyone cheers, you know. But that's not really the reason why they do their spins at the end of the routine. It's because like after you do that, you're super dizzy. Like, so if they did that at the start of the routine, then they'd miss everything, which would really be fun to watch, I think. But they never do that. They don't take my advice.
Would it be easier to maintain rotation with the mass close to the center of the mass?
To maintain it, it's no harder to maintain it. It's just harder to, and the reason for that is this determines angular acceleration, not angular velocity. Okay, so once you're spinning, if there's no friction or anything, you'd keep spinning forever, you know, in either of these two positions. But it's harder to get it spinning because it's an angular acceleration to go from 0 spin to whatever your final spin is. Okay. Well, mass moment of inertia also has an integral definition. And that is, so I sub A is equal to the integral over the whole mass of r squared dm, where r is the distance from this infinitesimal mass. Actually, let me write it in the other order. So from the about point A to that infinitesimal mass dm. So you can see there that as the distance of those masses gets greater from the axis of rotation, that mass moment of inertia gets bigger. Okay. The SI units of mass moment of inertia, you can always get the units from the definition. So this has units of kilograms, the mass. This has units of meters. So this is kilogram meters squared. And as an example, let's think about a disk. And we're going to deal with a lot of disks. And notice that this disk can rotate about 3 different coordinate axes. Okay, so it can rotate like a wheel, and that's about an axis like this. Or it can rotate about either of these 2 axes. And notice in that case, this thing wouldn't be rotating like a wheel anymore. It would be rotating like a paddle, flipping like a flipped coin, you know? And so there's a moment of inertia if this point is A, that tells you how difficult it is to rotate it like a paddle. That's both of these 2 rotations, and those are the same. And then there's the one axis that's different from the other 2. That's the moment of inertia about the z-axis, and that's, a wheel. Let's call it like a blade. That's the aerodynamic one. Okay. None of this takes aerodynamics into account. We're not talking about aerodynamics. We're talking about how mass is distributed. But you can think of it that way. Like, are you imagining rolling this disc, or are you imagining flipping it like a coin? Okay. But be sure you make that distinction anytime you think about mass moment of inertia. Well, I guess I better go get the quizzes. I think maybe for this one, well, I'll think about it for Friday. Maybe we'll do a simple example going from the integral formula, but really the ideas are pretty similar to the center of mass. It's just a different integral formula. So maybe I'll just start by listing out the simple shapes. Yeah. Anybody have any questions about that? All right. Let me run down and get the quizzes.
Is this open notes?
No, closed notes. But remember, this is like, this is the first one, so you don't